Welcome back, everyone. I hope that you had a nice break and are ready for our next keynote speakers. Our next speaker is Tomislav Krizan, CEO at Atomic Intelligence, Consultancy Director, Principal Consultant, and Trainer at Exist Management LLC. In this presentation, he will share 2 European-funded projects that use artificial intelligence modeling to address important challenges in medicine and health. The first project is a product development project that aims to improve the early detection of prostate cancer based on omics, MRI images, and other available medical data. The second project is a research project that focuses on modeling cell behavior and identifying why immunotherapy is not working in different types of cancers. Tomislav, the stage is yours.
I think she already said everything, so the presentation is done. Okay. So first of all, I'll cover a few different elements about motivation, why we went into this direction, what led about establishing different type of consortium to tackle 2 different projects. Prostate AI is essentially early detection of a prostate cancer, and it's one of the, it covers about 1/4 of all male cancer currently available. And the second one, as it announced, is focusing why immunotherapy is not working when it should, because realistically, immunotherapy should be tailored to a specific person, and it should work wonders, essentially. When it works as a charm, but there are quite a lot of different reasons why it doesn't work. So we took 3 different types of cancers so that there is no biases, so that we can find a variety of different omic, peptide, etc. data and see what are either gene mutations or other environmental elements which renders immunotherapy false in this case. So I'll go through the motivation and some of the numberings. So the first slide is essentially fully biased. Everything is about males. Why? Because we are talking about male types of cancer, and that's a prostate cancer in this case. And if you see, it covers about 1/4 of all cancers. There is a big issue with prostate cancer detections, etc. At the moment, everything is done invasively. There are some peptides and there are some markers which you can track, but they give a lot of false positives and a lot of false negatives. Only certain way to confirm is through the biopsy and dissection of tissue. The other issue with prostate cancer and maybe lung cancer later on, etc., is that you can't detect it if you are not going on regular checkups. The reason why? Because it doesn't hurt. And when you find it out, if it starts to hurt, it's too late. Like if you are lucky enough to detect it early, survival rate goes like 98%. And it has a slow progress. Even if you find that you have a low risk scoring and you are going into the prostate cancer direction, it still means that you have quite enough time until you reach the point of no return. So those are the numbers which are currently done on the European level, where you can see how many new instances of different cancers happened in 2022 when we wrote this proposal initially. This is on next one, I'll show on next one, we see that there is incidence versus mortality, which is different between different countries due to the fact how medical and health institutions works. Some of them are having a better approach on dealing with this type of diseases and had less mortality rate than the other one. Plus, there is this part of early checkups, etc., where you are going to the point when cancer is detected. The worrying part is a European prediction what will happen between 2020 and 2040, where we see a skyrocketing part of number of diseases coming and first of all being detected, number of the deaths, which goes even on a higher alarming rate. Again, we are coming to the point late detection. So a lot of people are even not answering a proper call to do checkups when you get it from the systematic checks, etc. Then when we start seeing distribution again between 20 and 20, we see that some of the modern countries have a huge jump. And all of those countries we picked as, let's say, guinea pigs during our project. So Germany, Netherlands, Spain, Italy, Croatia, etc., because they have a different volume and jumping between identification or incidence, and at the end mortality. And we see that there is a huge gap and a huge quantum leap on number of the deaths. And this is something which bears a lot of additional cost to each of the national countries, just trying to prolong the life of impacted males in this case. For other projects, it's a little bit similar, but we will focus on 3 different cancer types. So the other project is called Multir. We are focusing in this case both on males and females, and we cover lung cancer, spleen cancer, and melanoma, because they are completely different in behavior, but would like to do a modeling and see what are the impacts, or either environmental or in human body, which are rendering immunotherapy as not possible. And then we have the similar prediction where we see like a number of discovered patients will rise for about 20%, but about 32% of them will die, which means that we have even a stronger curve in this case, because we are talking more invasive cancers than when we talk about prostate itself. There are no newer numbers, so I took information from EU level about investment and the cost of treating patients from the cancer from 1995 to over 2018. As I said, there is no newer numbers available, but you see that there is a direct cost associated to in healthcare and indirect through other benefits or other elements impacting the whole treatments of those patients. Should I return it? Yeah, you're welcome. Now, I'll focus on the prostate AI. So it's essentially, we already got the codes, etc. It's a project which tries to do non-invasive early detection. So as I said, detection of the prostate cancer or confirmation of a prostate cancer at the moment is done through the biopsy. So we are looking at the ways how we can do this in non-invasive ways, and only when there is a high risk chance that you need to do a double confirmation, then you'll do a biopsy as a second step. So this needs to be, project aims to be something you could buy in any pharmacy, collect the samples at the home and send it in a reference center who will do appropriate process. We did some small pilot in US, and we got like a letter of interest from US government that when this gets completed, they would like to use this as a cheaper alternative, as a preventive to any type of cancer treatment. In consortium, there are 2 companies. There is a German medical research company and us, who are focusing on data side and AI modeling on top of it. German counterparts, they do have a lot of omic data already through different patients. And from the other side, they have a huge investment fund from their side, pushing them in this type of genetic and omnionic and proteomic type of research. So it's a really good combination because they are bringing a knowledge and expertise from the cancer. Secondly, they created one of the devices who is foundation, essentially it's a foundation for everything we are building on top of it. And this is element here, which does decomposition of urine samples. This is a high-level overview of what we are doing on the project. We have some mobile devices so that we are like a patient-first approach. You will buy a urine test in a pharmacy, take a QR code as a screenshot. It will guide you how to collect the sample, where to send it in a reference center for analytics. It will process, and on your phone, you'll get information back. Essentially, nobody knows your name or anything, so even if there are insurances involved, nothing got spilled, so it's completely GDPR or privacy confirmed. Secondly, you, through a mobile application, you can upload or take a photo of your medical paper. So if you did already MRI, or if you did some ultrasound, or if you already had a biopsy, if you come from the countries which this is a essentially initial step, and then you start going through all of those informations. We also started to create with both patient groups Q&A sessions, so that we can follow up with some additional questions which will give us more information into our prediction later on. So if some things are not fully clear from urine or MRIs, etc., we'll start asking about some demographics, some environment information, so that we can get as many as possible features to try to calculate a risk score for those persons. Now, initially, this is how a classical detection of the prostate cancer looks. On the left side, you see you'll do a PSA. PSA will show either elevation or not, etc. Based on that, you'll need to do a biopsy to confirm it. From the other side, we are working on something called the liquid biopsy process, where we are going through the urine test to collect and then calculating level of the riskness. And should you go into active surveillance mode, or should you be directed to the first medical facility, which will then cover appropriate next step medical advances. Existing urine tests which are available on the market, they always come after you do a DRIs, essentially digital rectum exam. When you do those, then you can apply additional urine tests. So it means that they are not tailored to cover different things. The reason why we started as a prototype, and I'll show you, we did it on a group about 1,357 cohorts of the data, and did check into two different elements, one with the primary cancer and then secondary with recurrence, when you have a relapse. And looking into those, we see that the first iteration really has a strong point of detecting. The reason is because cancer cells, especially in the prostate, get diluted, they start to shed, and if you have appropriate equipment, you can detect those patterns through the omics and peptides. So this is just a metric when we started to do box plotting to see each of those groups, in which direction should we continue, because initially, initial prototype was done the pure statistical way, and through the pure statistics you can reach some level, but for any medical applied devices you need at least 87% of accuracy to be able to use it in the medical field. So then we opted to go on a different side to collect all the proteins and peptides, see how each of them is responding to different type of diabetic or disease-specific processes. And the team, the other part of the consortium, are bringing knowledge of essentially movement into, on a cell level, how the proteins are moving information from point A to B. Now, why we are using urine in this case? First of all, it's really good messaging system, let's call it like that, if you focus on the informatical part, because it moves from your body in large quantities and it's not invasive. It also has really good secondary approach that it brings you information from your kidneys. So you can find the patterns and essentially links between two different organs in a human body, and from the same sample you can do multiple different elements. I think this is the part where all the males, I think yeah, this one. All of you who are a little bit, I would say, worrying, do not look at this one, because this is a traditional way. This is how at the moment is done. So this is something I looked at as the first picture after the launch. So this is how at the moment is done. So you need to get the tissue and then dissect it to find appropriate information. But again, it's invasive. Even if PSA shows wrong information, you need to do this to confirm is it wrong or not. So what we are trying to go is essentially a liquid biopsy concept. The company with whom we are working, they developed CEMS type of solution. So the next slide is a little bit better, because what they initially did, they are even now selling those as a kits if somebody wants to get the omics and peptides they're personalized. But we are taking those information to do different modeling on top of it. So they developed a solution which will first of all vaporize urine and then ionize it and look into spectral analysis of each of it. And during like 60 minutes of processing time, it can extract up to 6,000 different omic information, which we are then looking what is relevant and normalize the data to see how it fits and do we have some type of riskness. Now, this is just only one part of information. Because this will provide a numerical data at the end. But this is how it initially goes out of the system. So this is a patient 1, this is a patient 2, this is a patient 3. Over those 60 minutes, you see how the spectrally urine of each of them is spread. Now, each of those colors means how much is representing to the specific protein. And if you pull it back, you'll get something like this. Each of those numbers represent one of the elements, and with the value. Value represents essentially to the color. Now, the system can detect some of the patterns, and we'll get normalized data. But at the same time, if you focus on a vision part of the tools, this becomes also a better type of solution to use a spectral analysis and find different patterns and correlations between peptides and omics to get the result. Now, this is just a starting point. Then you start normalizing, and you will get data like this. Some of those data are provided by patients through the mobile interfaces. Some of them are done through already existing medical checkups. Some of them through the MRIs, like in this case, you'll have second two of them which already have a prostate cancer, first of all. No, so you have a lot of additional, let's call it sources, which we use to confirm something if you have information. Not all patients have MRIs, but they can do urine tests. They can provide you some additional information which we then take for computation. From the other side, for the multi, we had a little bit different approach. There are different immunotherapies currently done on a level of EU, and it's focusing a specific cancer type and subtype. And this becomes an issue because you are trying to go in tailor-made treatments. They are quite expensive, but if they work, they work. For those who your life are trying to save, this works wonders. For those from the other side who will pay it, it's a little bit hefty price, especially when you see what needs to be done, and then from each of those immunotherapy approaches, maybe 80% of them will not work. And at the moment, it's not known what are those features or what are those values or behaviors which render immunotherapy as non-valid. So this is one of interaction where from the normal cells, when it starts getting cancer, how it spreads. We went in a different direction. This is essentially a consortium of 17 different companies. I think the next slide would be better. 17 different companies which are covering different type of expertise. Our part, again, is a type of the data and type of the modeling, plus a team from University in Dublin is providing a statistical information to us, and we are, let's say, piggybacking on their work, which they did announce in October last year. Two of those professors from Institute in Dublin are also teachers in Stanford University, and they came out with a paper, and not just paper, but a mechanistical model of a human cell called C-star. I'll jump a little bit, just to show you those 16 covering globally and even from the US, Canada, etc. So it's a big collaboration in this process. 16 of them are essentially medical faculties and research institutes, plus we have 2 different government bodies which are providing patient type of a collaboration so that we can put also emphasis on patient and get their feedback on a solution. As I said, the first tool is more product-based, which is focusing on the patient. This is more focusing on doctors and researchers, which will then decide and specify next stages how the cancer should be treated when we find the root cause why something doesn't work. So that's aim, trying to find the root cause why something is not working. Again, it's a multimodal data, different type of cancers. We are still focusing on the collection of the urine, different type of fluids from the body as well. We have MRIs, ultrasound, etc. So a bunch of different data sets coming because we are talking about different sets of medical exams. But at the same time, we are piggybacking on mechanistical modeling done by University of Dublin and a C-star platform. C-star platform, as I said, it's a mechanistical model built statistically to work only on one use case. So you need to train it to work only one use case, and it will behave only for one. So that's from one side limitation, and from the other side, it's really strength. What we are looking here when we start working with this one, C-star is focusing on charge of electrical cell. Healthiness of the human cell can be measured through the charges, and it's called Valence field, how the charge goes between healthy and non-healthy human cell, and you can then track and measure this to see how well you are as a person. And then from the other side, we are collecting different elements, gene mutations, omics, etc., to see which of those environmental and or demographic parameters are rendering that you are stuck in some point in that electrical charge level. So what we focused also, this needs to be on an open science, like an open science practice. All the data will be exposed after the project is done on a European level as a data set, so anybody who wants to continue will have an access to the data, both to the data and the model. Models will be trained in an anonymous way so that you don't have any patient information inside of it. The concepts we will use is federative learning so that you can pull the model and do additional training with your own data, which you may have in-house, so that you better tailor the solution going forward. And this is in line with the European Union. European Union is now looking in all the funds that as a feedback or as a return, they get both models, they get both data sets so that other can continue on that same practice so that there is nothing proprietary which you can't use. The first product-based, it's a focus on product, and there is IP and there is a proprietary information and it's a product. You don't need to submit anything, but this one is covered with 100% of the grants, which means it's a pure research project. And we got about 100% of the points for this project as well. Now, the focus on ML is that we try to use the SMILE approach about simplified molecular line input, which is essentially modeling every molecule and putting it as a set of the features in a graphical neural network, aligning with the parts from masked input and aligning with the C-star itself. So we took a Bayesian molecular approach for statistical part of C-star and then try to automate it or make it dynamic so that we can cover more than one use case. At the moment, C-star is really focusing on one element. So if you want to cover different gene mutation, you need to build 10,000 different C-star molecular or mechanistic models and then try to combine them as a single output to see something, is it rendered valid or not. This is one of the elements how we also went with the SMILE approach and trying to see how the response will be happening on each of the peptides or omic or gene manipulation, mutation based on a drug applied at that specific point. So there is counterparts and there is interaction in those systems because we are talking about complex systems. Question is, can we model all of it? But our goal is to try to find outliers. Now, there are some future extensions to both of those projects, and we already started to explore them, and we already started to push two of them, because two of them you'll see now in the list, who are following the similar principles, but now are focusing on a different data. But it still has a data. Some of them are patient first, some of them are, again, more like on physicians rather than on patients, depending what we are trying to do. This is a project which is currently in evaluation. We're trying to see how different, let's say, vessels in your bloodstream, etc., can impact two different chronic diseases. So your kidney chronic disease and your cardiovascular approaches, because again, both of them can be measured, both through the flow and different omic set of information, and plus it can through the modeling of charge on a cell level. The second one, which we are just talking and trying to align, a process is to see how, for the people who already have immunocompromised environment or organism, some of those modern diseases we are now seeing can impact and start that perfect storm in them. Like COVID, when it started, it hit anything what is wrong inside of you to the point where you died. So essentially, it's just escalating whatever is wrong in the human body, and this is one of the elements we will try to model and try to see on a cell level what will happen if you do come with this one and you have those type of information. The second one, which we are currently doing with the French faculties, and it's in preparation, it's a modeling for diabetes type 2, obesity, and how, again, there is a link between COVID. We have a set of the COVID data between dietary approaches and environment approaches interacts with your diseases like diabetes or obesity, and how it elevates those, because it can escalate. We have a set of the data of the people who are only eating fish, because that's their therapy. So there is quite a few interesting cases, especially from the data side, what you can do, et cetera, et cetera. And similar like a prostate cancer, there is a blood cancer approach. It's a different peptides, but still you can model. So it's quite evolving. One of the elements which we started with PepperKit, we started to create a new classifiers. So to extract and start measuring, because each of those classifiers can focus on the different types of cancer. So from the information you are looking at CKD classifier, it can point you in a blood cancer, bladder cancer, etc. In this case, cardio issue with your heart, so with HF2. So again, you are getting nothing more than a visual representation of some of the metrics. And after that, you'll do some normalization, et cetera, et cetera. And I also mentioned a bladder cancer. So this one is done similarly. We already have 3 different institutions with enough information, enough patient data so that we can start modeling, but it will come at some later point. And I think I'll stop here for any questions. Thank you. Milos.
Thank you. So regarding first project product, how do you control when it is good enough so you can guarantee lowest amount possible of false negatives?
False negatives.
Yeah.
Okay. So there is quite a few, quite a established metric from level of governance in EU, which renders that 87% is your lowest limit of positive, so which means that you cannot go up to 10% appropriately false negative, but it's still wrong. What is biggest now, let's say, we have a technical auditor on the project. The biggest hurdle at the moment is trying to define appropriate peptides level, because this is still field in research. Luckily, from prostate cancer side, the company who is doing omic detection, etc., is in the field of the cancer and omic detection for last few decades. Member of their board is on a level of the European Union in charge for defining the strategy how cancer will be treated in next decades, etc., etc. So there is quite a lot of research happening on a daily basis, and there are quite a lot of tweaking on a daily basis. So as I said, we did the prototype, and the full project started like half a year ago. And the first part of the project was mostly now scaling to put a data management platform so that when you do MRI, when you do your medical papers, etc., it will do anonymization on the fly and connect you as a number, which I showed later on, so that you can get your information back. Will there be changes? Because it's a 3-year project, definitely it will, because first of all, field of medicine is evolving. Secondly, field of AI in medicine evolving on a daily level. So quality, we aim high, but we have a lowest level of acceptance, which is prescribed on a level of EU.
One more, if I can. Are you open? Yeah, I have a very good friend. He did PhD in very similar field. So are you open some new collaborators in coming years?
So this is something we are doing as our also internal, let's say, research, because for years we are doing different types from the vision, audio, language, etc. But this starts to pull all of those elements of AI in a single box, where we needed industry expertise. Yes, we worked in those industries, not just medical, but the other one, on some analytical layers. Now we are trying to move a technology to go on a cell level and behave as a digital twin, because then you can do a lot of validation before you start in the next phase. Last phase of Malta project is we do in silico testing, but we'll do in vitro as well. So there will be mice testing at the end after we are done with all the mechanistic models to validate this on a living tissue as well. That's a double-blind approach. Anybody else? Then we can start charging exit. Thank you.
Thank you very much, Tomislav, for this very insightful talk.
Thank you.
This is your certificate of appreciation for your engagement at DSC
Thank you.
Europe 23. Thank you very much.
Bye.